Okay, hello everyone, good afternoon. Um, I think this is the last discussion. But before we continue this related rate, I would like to start with my exercise. Have you checked in the Moodle? Have you checked? No, right? I would like to maybe solve some few examples from here, in which you find maybe quite confusing or perhaps quite difficult. Okay. Have you tried a few questions? No? Okay, maybe try now. Maybe you could try, I don't know, maybe look for a moment and then let me know which part you need to solve. There are some parts that is actually a little bit long. So I hope you try solve this, and I will provide the answer key, but maybe later. Because the answer key will be useless if you are not trying to solve it by yourself. So try first and see which part that you're still having some difficulty with. Number one, okay, right? Not really complicated. Number two, although it will get you to some problem, but I think you still can solve it. Although it's quite, I think it's a little bit long because of the structure, the fractions you get. Number three is too easy, right? Number three easy. Even you don't need to calculate. So if you have 5 with power sign, remember any constant with power of function, then we are going to have this original equation as in the derivative. So the derivative will be 5 with power of sine, and then multiply with the L and the constant 5, multiply the chain rule, which is cosine, and that's it. Number 4, find the tangent line to this curve at this point 0, 1. Find the derivative of this. I think you can try this quotient rule, or you can put this going up, but I think this quotient rule is very easy. So you have this squared, and then this f prime will be 0, so 0 minus, and then you need to calculate the derivative of the denominator, and you will get the result, right? I think the most difficult part is, I think, around 7 to 9. 7, 8, 9. Number 5, find all points of the function, blah, 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 at which the tangent line is horizontal. Tangent line horizontal means the derivative, or dy dx, equal to 0. Okay? Maybe to start, let's try number 6. Okay, let's try number 6. Chain rule number 6. Okay? Chain rule number 6. So let's focus on number 6. Let's try number 6. Okay. So you have some composite functions. You have a function multiplied by 4, and that 4 is inside another function, which is another f. And then it's multiplied with another constant 3, which all of them are inside the function of f. We don't really know what kind of function is that, but we know that if we put 0 to that function, it will be 0. And for the derivative, if we put 0, it will equal to 2. So we need to calculate the derivative of this capital F at x equals 0. Okay, at x equals 0. So, how to solve this? Maybe let me give you a couple minutes to try. Okay? It's a little bit complicated, but as long as you write the whole process and you didn't miss any process from the beginning, you will get the answer. You'll get the answer. There are no shortcuts to write the process, so you need to write everything. Anyone got the number? Slowly. Okay. Anyone got the answer? How about this side? Have you tried? Okay. The answer should be 96. So let me put here the f is okay, so f capital prime, okay, f capital prime, so f, and then multiply with the chain rule of the inside, which is 3f for f of x, okay. And then this will be 3f for f of x, and then 3f prime for f of x, multiply with ddx of 4 f of x, or we can say directly this is getting 4 f prime x. So we put x equals 0, so put x equals 0, so f prime at x equals 0, this will be, so with the 1 0 here is f0, so f0 is 0, so f0, so this whole thing is 0, so 3f0 also 0, so this is whole thing is 0, which give you f prime 0 is 2, and then 3f prime, this is 0, give you 0, this is giving you 2, this is giving you another 2, so 2 with power of 3 multiplied by 3 multiplied by 4, which is 96, okay. So the basis is if you have, like, for example, like the function capital F, which is based on the composite function, the derivative of this will be, we derive the outside function, we put everything inside, and then multiply with the derivative of the inside, okay, which we are going to set everything here, like peeling the onion, where we start from the outer layer, and one by one we get into the inside layer. Okay. So we start from the outside, which is this whole thing here. So we derive as it is f prime, and put everything is inside. Okay? No need to manipulate or maybe change this inside here, and then multiply with the derivative of the inside here. And of course, this has another layer that needs to be broken down, right? We need to peel the layer again. So this part, we are going to take the layer like this, 3f prime for f of x, multiply with the inside function, which is getting the 4f prime x. I hope you get the idea. It's from here, we implement into our functions here. So we start from the outside, we break down here, up until we get the most inside one. So we start from the outside and then the inside here. The question is number 6. Okay, number 6. Oh, I need you to choose which number you feel that need to be explained, like more explanation. Any idea? Which one? What do you think? Number 8, yeah. Okay, good. It's quite long. Okay. Number 8 it's quite interesting because we have x and y within the equations, which we are going to have a tangent line that is equal to -1. And then we need to find which point. It could be several points. And we need to find out what kind of points we have. So we start off by taking these equations and then implicitly derive, implicit differentiation. So we are going to set this like a product rule. All this x squared, y squared, and xy we set as a product rule. So let me write in a new page. Let me write. Here x squared, y squared plus xy. Let me check. Equal to, and the slope should be -1. So equal to, and then the slope is -1, or we say dy dx is equal -1. Okay. Okay. Now we start from taking derivative of these equations. So this will be start 2x y squared plus x squared 2y dy dx, right? Let me put a little bit to the left here. And then plus y plus x dy dx equal to 0. Okay. So I will combine these two. So 2x squared y plus x and then what else? Let me put here -2xy squared -y. And then this dy dx is equal -1. Okay, so let's put dy dx equal -1. So this will be negative, right? And we can put also negative here, which we can see that we can remove the negative. And then what else? I think we can factorize x. Factorize y. Interesting, right? Can we cancel this? Can we? Okay, what happened when we cancel this? Maybe we are going to lose some solutions. Okay? So I think it's better just to keep that. Okay? So we are going to solve this like our factorization. So we're going to move to here because they have the same factor, right? So let's just move to the other side. So we can write so we are going to have okay. So we have two possibilities. So the first possibility is 2xy plus 1 equals 0. Okay. So 2xy is -1, xy is -1/2. And the other one is x minus y equals 0. Or we could say that this y is equal x. Okay. So we have these two possibilities. Let me write the question again here. We have the x squared y squared plus xy equal 2. So we can check. Let's say at xy equal -1/2, then this will be -1/2 squared, right? Minus or plus -1/2. Let me just write here whether it is going to be, this is 1/4, this is -1/2, which is it equal to? No, right? So this is not satisfactory. So perhaps we try y equal x. So at y equal x, so we can exchange x to y or y to x. We can write x with power of 4 plus x squared equal 2. And I think we can factorize this, right? So this will be x squared plus 2 minus 1, right? Okay. 2 minus 1, okay. So we have another possibility, right? Another possibility. So x squared can be -2, which is not satisfactory for the real number. So not satisfactory. And x squared equal 1, which x is going to be plus minus 1. So we can check, again, we can check this plus minus 1. So when x is equal 1, then y is equal 1. So we could check inside our forms, and I think it's satisfactory, right? So it's satisfactory, so let me just write like that. And then when x is -1, y -1, we can also see that all the terms going to be satisfactory. So this is also satisfactory. What is our goal? Find the points or find what? Find all points. So the points, points that's satisfactory. That's satisfactory are 1, 1, and -1, -1. This is the answer. Okay, quite crazy. Worthy to be in your exam. Anyone tried finding the answer? Did you get the answer? Or no? So it's somehow from derivative and then we get some algebra. process here, this is based on your algebra. This is not your calculus. This is algebra. Only for sentences. The calculus part is up until that one, the implicit, that's the calculus part. To finish off that, we need some algebra. The top. Yeah, this one, the calculus part is this one. Okay, this is the calculus part. The rest is basic mathematics, algebra, and some sort of that. And now you are thinking about your future. Can I pass this course? Like, of course, I will give you like complicated question in exercise, so that you can move forward, and it will give me maybe some ideas what kind of exam you need. Not what kind of exam you want, but of course you need. I think for your references, I will attach later either last year or maybe last 2 years midterm. I think midterm on 2021 or 2020. The midterm are, I just realized it's too hard to do, but I think it's good for exercise. But I think last year is okay. The midterm is okay. Okay, any other questions? Which number again? Maybe one more number and then we can move to our sections. Okay, let's put back the number here. So any idea which number you feel that you need to be explained more, elaborated more?
Can we do number 9?
Number 9? Okay. Yeah. The solution is crazy. It's like really big. But I will give you some suggestions to number 9. Okay, let's start number 9. Number 9. E with power of negative x cosine squared over x squared plus, okay. So let me start with writing e and then cosine squared and then x squared plus x plus 1. The question is asking the first derivative. Okay. I think I mentioned in class several times, like, there are many paths. There are many paths that you can take. You can directly, okay, it's a fractions. Okay, let's do the quotient rule. But do you want to do the quotient rule? But it's up to you. It's doable. You can do quotient rule, but you can do also some arrangement first. So you can rearrange if you see anything that maybe you have you see some patterns in the structure, and then maybe you could break down the structure, and then maybe it will go more simplified. So that way also goes okay. Both method, either you do the calculus and then algebra, or algebra first and then calculus, they have the same result. They have the same result. Okay, any idea how to solve this? This question is in your textbook in sections on logarithmic derivative. So you could see that is a clue. It's on the logarithmic derivative. So that's how you rearrange the structure. Maybe try for a while. Okay, try. Maybe 2 minutes. Try sometimes.
Oh. It basically is this positive point.
Yes. Okay.
Anyway, yeah, it's quite complicated, but idea is either you can try the quotient rule, like this, or you can rearrange this structure. But this way is doable, but perhaps it will make some difference, but still okay. You can try if you want. Okay, one way to solve is by quotient rule. So let me just write the quotient rule for you. Maybe write the original quotient rule if you have f over g and you want to derive this. This will be g squared f prime g minus g prime f, right? So basically we can start by taking the denominator as with squared, and then let me just put the dx of the e and then multiply with x squared plus x plus 1 and then minus the dx of x squared plus x plus 1 and then multiply with e. Okay, so you need to find the derivative of these two forms, okay, and then you can simplify it and then that's the answer. Or I will show you that I think I will rearrange the structure. So let's write y equal and then I will add log both sides, so ln and ln. So ln y equal to okay. And then what's next? Next is, let me write ln(y), and then we can rearrange a over b becomes ln a minus ln b. Okay? And we can rearrange these two. Okay, it's these two property on logarithm. So we can rearrange this part here. And then arranging this part, taking the and then we get some, I think, good structure to be derived. Ln e is becoming cancelled, so this will be negative x plus ln okay. What's happened next is we are going to implicit differentiation. This will give you 1 over y dy dx negative 1 plus 1 over cosine squared x, and then chain rule. It will be, let me write here, 2 cosine x and then sine x, and then need to be minus, right? So and then minus 1 over x squared plus x plus 1, and then 2x plus 1. And then dy dx, we can multiply all with y. So y is what? Y is our original equations. So we can write multiply with negative 1 minus 2 cosine x sine x, or we can, I think we can solve this cosine with this cosine over there. So negative 2 tangent, so we can have negative 2 tangent. And negative 2x plus 1. Okay, I will just stop until there. And then that's the derivative. If you want to make it positive, you can write the negative outside here. So negative, and this will be all positive. Yeah, I think whenever you find any fractions or any product forms that you can break down, you can try adding logarithm, adding log. Okay, any question from this one? Anyway, if you want just to make sure that your derivative is correct, you can go to the Wolfram alpha. Okay, I show you at the beginning of the class, but I don't think you are going to open it, right? It's just a website, so you can right now you can type in Wolfram alpha. So let me write Wolfram. Okay. This is basically mathematical computation. Not only mathematics, that you can ask everything. You can ask anything. You can ask anything. Like if you know the ChatGPT is similar to that, but it's not an AI. It's basically computation. So you need to write your equation if you want to ask like something related to math. You can ask like find the derivative of, and then you put the functions. They have the calculators that you can put the DDI, something like that, and then it's right. Okay. I don't know why kids nowadays doesn't have curiosity to find out anything new. It's right. It's fun. It's fun. It's like when you play the ChatGPT and ask like weird questions, and it's sometimes answering like really good. Sometimes he's hallucinating. Okay. If there's no more question on this part, then we are going to continue the last one, the related rate. Okay. Just for a few more examples, and then we can move to the next section, which is the linear approximation. The last part in chapter 3. Last part in chapter 3. So I have prepared the answer key for all the questions like this. Okay. Okay, so later I will put in the Moodle, okay? So let's back to our notes. Okay, back to the related rates. So the next example that I would like to show you is the shadow problem. Okay. So a man walks. I give you this illustration to help you to visualize what is happening and what you need to compute. So a man walks a straight path at a speed of some number 4 feet per second, and then it has a spotlight located on the ground 20 feet from the path. Okay. You know spotlight, right? So the spotlight will spot on to the man. When the man is walking, it's going to follow the man. Okay, it's going to follow the man. And then the question asking is at what rate the spotlight is rotating. It has some rate, okay? The angular velocity, some sort of that. Right? But in this case, you can think like we did the inverse of trigonometry. We are actually taking the derivative of the angle, right? Y equals sine inverse, meaning y is the angle, right? So actually, dy dx for the inverse of trigonometry is actually the rate of the angle itself. Okay, so that is what we are going to do. Okay, so we are going to find this theta dt. Okay, so right here we want to find this d theta dt.
So d theta dt when the man is 15 feet from the point. So it has variable x. So it's asking at 15, what will be the rate? So of course, to break down this question, we need to set some relations between all of them. So set the relations.
So if we have the theta, we have x, and we have the 20 as a constant. So we have a triangle. So we have a triangle. So this is theta. This is x. This is 20. So we can set that tangent theta is x over 20. So we can set that x is 20 tangent theta. And then that's it. We can derive this with respect to t. So we get dx dt equal 20. Derivative of tangent is, anyone remember? What is derivative of tangent? Secant squared, yeah. Secant squared theta d theta dt. Okay. Now dx dt is 4, right? So this is dx dt. And this is the, or I think we can just put inside. So dx dt, so d theta. Oh, we need to find the angle. We need to find the angle. So when x is 15, so we have this triangle, right? So we have 20, we have 15. So it's asking what's theta here. Let me finish off this and then we can have a break. So we have 400, and so this will be 625, so 25, right? Okay, Pythagorean, with Pythagorean is 25, which means that the secant is 1 over cosine, right? Cosine is 20 over 15. Is it correct or no? Okay, I think correct. Oh no, 25, sorry. So secant is 25 over 20. So we have 20. This is 25 over 20 squared. D theta dt. This is 4. So this is 4. This is 5. So d theta dt will be, this will be 5, 4, so 25 over 4. Or 5 squared is 25, 125 over 4. So 16 over 125 radian per second, okay? In this case, we have someone walking and we have the spotlight. Okay. And the problem here is the spotlight is rotating and the question is asking how much the rate is. Which means we can see the rate for the rotation. It's basically the easiest way is to see the angle is changing. So we can take that as our clue to make that the question is actually asking the rate of the angle, the angular velocity, right? And then we have everything, all the numbers, like the distance, and actually it's asking when the man is at some point, at some distance. Okay? So we can take that as our, using our trigonometric relation between the theta and x. Okay? We can take that relation. Another way, which I just remember, we can also take the tangent inverse like this, and then we have this expression. So we can take the derivative of this. This will give you the same result. So there are also multiple ways to view. As long as your relation is correct, confirming, and all the assumptions also correct and consistent, you will get the same result. Okay, that's practically 5 examples that mostly you will have. Okay. I prepared some questions here for related rates. For example, this one we have 6 questions. So you could see first, and I think you will know how to if you try to solve it. Okay. So you have 6 questions, and yeah, maybe I think the first 3 should be not too complicated. Like number 15, it has the similar problem, but it is asking the shadow, the rate of the shadow. So there's a line, and when the light passes on someone, you have your shadow, right? And when someone is walking, the shadow is also moved, right? And you need to define the rate of that shadow, something like that. So the idea is you need to have a basic geometry, trigonometry, and also understanding what the goal is in the question. As long as you understand all of that, I think, and you can relate all the information within the questions, I suppose you can solve the problems. But of course, I think because we are not all native in English, so I believe some clue for some diagram, some scheme, I will provide. Okay, in the exam I will provide. But try your best. Make your own assumptions. Okay, for this case, for the 6th question. Later I will give you also the answer key for these 6 questions. Okay. Okay, I think we are going to get more practice also on the TA class. Also on, I think I will prepare another exercise next week before your quiz. Okay. So yeah, I will solve these questions. Okay. Now we need to move to new sections. Okay, the linear approximation, which is still related to the tangent line. Okay, if you already have taken photo of this, you can take photo and then later you can try yourself, okay? But now let's see this linear approximations, okay? So what is linear approximation? So approximation is we want to estimate something, right? But most of the cases we want to estimate, for example, this curve here, the blue curve. So we want to estimate through this straight line. If you see this curve, okay, this blue curve, the more it is going to be closer to this point, you will see that the gap between the tangent line and the curve getting closer, which means that at this nearby point, you can estimate the curve through the linear equation. Okay, and the more we have
here, for example, far away from the point, this point here, the tangent point, the gap is getting larger, right? So in terms of approximation, it's getting not accurate at all. Right? So the more we have closer and closer, we're going to have like more accurate. Okay.
So let me write here, just to remind you the algebra of the slope point. We have y. We have this, right?
M is the slope, okay? X1 and Y1 is our point. Now in calculus, we learn the tangent line, which is actually the same structure with our slope point form. Okay?
Now we have in calculus, we learned that actually our m is our y prime. Okay? So we can write this as y okay. So based on this picture,
We can try to set up our own line equations through this singular structure. Okay? The same thing. So we can write using the f of a, and then L of x. So the line is L of x.
so we can start with maybe the general structure. So equation of tangent line. So from here we get that y equal f of a, or maybe let me write y minus f of a. So this is at x equal a, okay, equal f prime a and x minus a. Or we can write y f of a plus f prime a x minus a. And we can write the y as a linear function L. Okay. Okay. So we can write as L of x this is what we call delinearizations.
So what is the whole point here? What we are going to do? What is our goal? It's not as like a random linear equation. Our goal is actually we are going to set up this L as our function, the blue function, the blue curve, f of x. So we can approach f of x, getting closer.
Quite trouble. It's really sensitive, the cable.
Okay, so we are going to approach f of x from point A using our red curve. Okay, so if we put, so we can say like maybe we would like
To say, let's say, we want to know the square root of 3.98.
okay, we want to know this result. Of course, you could plug in into your calculator, you get this result. But we can use calculus. We can use this approximation. If this is 4, this is 2. Okay? If this is 4, this is 2. And we can imagine this as a function of
Square root of x. Okay?
the function of square root of x. So we want to know like if we would like to calculate this, can we try some approximation?
So let me give you some idea here. So we can put it here. So let the function is square root of x, and we have the f prime, which is 1 over 2 squared x, and then we can define the linear. This is going to be f a plus f prime a, and then x minus a. So we would like to get a
as some numbers that we can produce easily. For example, 4. Okay, yeah. If we square 4, we get 2, right? So let's take a equals to 4. Okay.
So let a equal 4.
So we can take 4 inside here. This is 2, so this is square root of 4.
Plus, and this is actually the delta. Okay, let me write, maybe not x minus a, it will be confusing because of the positive negative. Let me write as a delta. Okay. So the delta,
To get 4 to 3.98, we need to minus 0.02, right? So we are going to write the delta is minus, okay? Because if we say it's plus, it doesn't make sense. It's not logical, right? It's not logical. Because this is less than, should be less than 2, right?
so we are going to multiply this with negative 0.02. So we have 2 or this is going to be so it should be 1.5. Is it? Yeah. I don't know.
Is it, if you square this, do you get closer to 3.98? Can you check your calculator? Just square this one. Square this one. Take the square. Multiply by itself.
3.90025.
Okay, this is quite good. So it means that we apply calculus into our calculation. Of course, the calculus part can be also implemented for some
Simulations that may be more advanced, like finding the error. Oh. Okay.
This is some applications that we can use. Okay. So I think this is the default. Okay. The default. So again, it also depends. Like this x and a can be switched. Like this case is actually a minus x, or you can see that this is going to be a half reduction. For this one, we assume that this is going to plus, right? We are going to assume that it's going to plus. Okay. I hope you get the reasons behind this.
So basically, we are going to have a function that we want to approach.
Okay. So this is the function that we want to approach. Okay.
This is approximate by the line equations. So this is what we call the linear approximation. for example, another way, the same function, but let's say we try to find 4.01. Okay? We try to find 4.01. So the same thing, we can approach with a equal 4, okay, because 4 is something that we can square easily. And then on the last part, we need to add. So it should be 0.01. 0.01. So same thing here, but this will be 0.01. Okay. This is 2 plus 1 over 4. So what is that? 0.25. 0.25 divided by 100. So this will be around 2.0025. Okay. In chapter 4, actually there are another approximation similar to this in chapter 3. So I think I will give you now just as an introduction how to find it, and then we can review later. So yeah, basically that's it, the linear approximation. Another way to look this linear approximation is basically with the differentials form like this. Okay? We call this is the differentials. So basically the same idea. So what we can get from here is actually we can write we write differential first. What is differential? So differential is when you have dy dx equal f prime x, we write in each term, each side with the dy and dx. We call this a differential forms. Okay. Now if we look at the graph, when we start from x, we start from point P, we add some delta, okay? And when we add some delta, as a consequence, for the curve that on Q, we also get some additional delta, okay? Some additional delta from P, okay? Get that. But then we also know that at this point P, we are approximating the curve with the line. Okay? And as I mentioned, when we are taking far away from this P, we get some gap, right? So the gap, let's say the gap is going to be defined by this dy. Okay? Now, we can rewrite our linear form as delta y by just taking the picture is basically equal with the difference between these two f.
But I haven't right answer.
So this delta is basically this f, okay, the f of the x plus delta x minus the f of x, okay, is here. So this is going to be that minus that, okay. So we can actually represent the equations with this differential form. Okay. For example, if we have f of x, let's say we have a polynomial x cubed, plus x squared minus 2x plus 1. Okay, and we say that x is changed from 2 to 2.05. Okay, it means the delta is 0.05. Then we can say that we can check the f of 2, which is 2 of 8 plus 4 minus 4 plus 1. So this will be 8 plus 1 is 9, right? And we can get the 2.05 from the equation. So you just take some time to calculate this. I just want to show you how the delta will be related to the slope. Okay, and we get this if you calculate. Let me just give you the numbers. So delta is basically the f minus f of 2, which you just practically subtract this 2, is equal to 0.717625. And for dy, it's actually our f prime x, which is we derive the f prime, become 3x squared plus 2x minus 2. Now we write the system as the x like that, and then we can approach the small changes. We can approach the small changes, which is dy is 3, 2 squared plus 2, and then minus 2. And then the small change from 2 to 2.05. So we can see that this is from here. From here we get the delta x, or the dx. The dx is 0.05. So we assume that the small changes is 0.05 based on the information that we can put into our equation here, which gives you 0.7. So you see that our comparison between the delta and the d, as long as you have a good approximation, you will have a good result. It means that we have differences about 0.01. 0.01. Another question is to see the differentials. So we are comparing the delta and the d. And then you can also check if you change the question, not the number. Let's say we change 2 to 2.01, and we make it smaller. The error will be also smaller. The error will be smaller. So the small dx will be, the results will be getting more accurate. Okay. So basically, this is chapter 3, last part, chapter 3. Okay. So basically, you can also, perhaps you can try from your definitions. Okay, so if I have y equal f of x, let's say at x equal a. Maybe if you want to write the notes here. Okay. let me just write some notes downside here. I will explain later. So this will be okay. Another perspective. If we take y equal f of x at x equal a, and we say that we want to take derivative and then put x equal a inside, we get the f prime a, which in our definitions, as we learn the derivative, it is actually the limit as x getting closer to a, f of x minus f of a divided by x minus a. This is the definition. There are two definitions. This is one of them. The other one is using the x and then x plus h, and then h is as a distance. We are taking the x and a. Okay? Because this form is actually quite similar to what we have in the line equations, right? So what we do in the linear approximation is actually in linear, so in approximation, we force out this f prime a to be forcing to be similar with the f of x minus f of a, so that we get the f of x minus f of a is getting approaching this, okay, which finally you get the same component of your linear approximations. Okay? So basically this is what we do in approximation. So we force out that the derivative is equal to the second formulation from the graph. Okay. So actually, the limit is helping us to get rid some small numbers that is too small and too, not really meaningful. The small number that's not really meaningful. Okay. But if we want to approximate, it means that we want to know like the exactly like how close is it. Of course, the approximation will have some errors, but the more the smaller errors in our system, meaning our system has a better result because it's getting similar to actual value. Okay. Okay. Now from this part here, from this approximation, I would like to bring to another method. Using the same principle. We call the method is the Newton's method. In your textbook, it's on the chapter 4, but I will bring here because it's actually the same principle. Okay. So the Newton's method is basically we would like to know, like if we have a curve, we would like to approximate the roots of the curve, whether it is going to be maybe let me just write in the picture. Okay. So let me copy this. Okay, so let me write here that from this part, so imagine we have some curve, okay. And the curve need to be crossing the x-axis because we would like to find the roots. Okay. So our goal is we would like to find
what x that is crossing here. Of course, it should be any random function that we are not supposed to be like knowing directly what kind of roots we have.
So we should write here. So let me write here is our goal. So what can we do? So first,
you have like maybe some polynomials. Maybe we could try some numbers. We put some numbers, we put some numbers. And what happened with our graph? Let's say we start from this. Okay. Maybe I will make
a little bit horizontal to make it nice and clean. Okay, maybe like that. Okay. So let's say we are going to take, let's say we start from here. This is, oh, why it's gone. This is x0. Okay, we start from x0. It's a little bit far from our goal, but let's say we are going to start with x0 because we are not sure what kind of graph. This is just illustration, so we just like try some random numbers like we think that is similar. We try x0, getting through here. At this point, we have a tangent line. Right? We have a tangent line. The tangent is going to be that. Okay,
let's say that's our tangent line. Okay, and the tangent line also crossing the x-axis. You see that we now have some number that is closer to the roots. Okay, let's name this x1. Okay.
Name this is x1. Okay, and we try another one. We try x1 and we get here.
Okay, and at this point here we also get a tangent line and it's getting closer. Okay, and I think because limitation of the pixels, you'll see that this is almost getting closer. And if we take maybe another x, so let's say this is x2.
So let's say this is x2.
Maybe we could take until 3, 4, 5, and you will see that it's getting consistent, the number, which means that we get the roots. Okay, we get the roots.
So the idea is we start from here, start from this. Let me just put down here. How do we find roots? How do we find roots?
How do we find roots? When what? This is the x-intercept. We find when? Yeah. When it's 0. Yeah, when it's 0, okay? When the f of x is 0. Like when you factorize, right? You factorize, find the roots, okay?
How to find roots is we take f of x equals 0. Meaning we have these equations now, right? And then let's rewrite the equations become x minus a become that. So we have x a minus of this, and then start the iteration. So start iteration from a equal x0. As we mentioned here, the x0 is our starting point, and then we get the x1, x0 minus and then suppose we have the x1, then we can try another x using x1. So all change with x1. And then we can have another x, x3, which comes from x2. And so on and so forth, okay? You will see, you will get the correct result when you have some consistency in x, okay? Maybe it will be 1.5, and then it's still 1.5 something, but it's still like 1.5 something. Maybe that is your answer. Sometimes you need to do it like maybe 6 iterations, 7 iterations. So basically, what you need to do is just plug in the number, plug in the x0 first to your function over the derivative of that function, and put in the x0 inside. So you need to use some time to calculate. Okay? So this is what we call the Newton's method. Okay. So let me write here, Newton's method. So we start, this is chapter 4, where I start from the Newton's method first. If you look your textbook, this is on Newton's method, chapter 4. Why I bring the Newton's method at the beginning? Because it's related to the linear approximations. So that we have two methods directly. Yeah, chapter 3, only for the techniques differentiation. Because the techniques only. Complicated, but the idea is we want to set some numbers, the numbers, when we take the linear approximation with the tangent line, it's crossing with another new x. Then when we use that, yes.
When we can understand that we found
you will see when we have the good numbers of iterations, you will see the numbers usually maybe it's 1.211 and then 1.2001 and then 1.20001 and then it's getting closer to that number and then it's consistent. It means that it's around that approximation. It will consistent. Yeah. Later I will show you. Yeah, any questions? Any questions? Yeah, Thursday.
Okay, before we end, let me write some questions first. The question will be elaborate on next Tuesday class, okay? Or maybe in this Saturday. We have class this Saturday, okay? Oh, yes, we have class 10:20 to 12 in this room, okay? So let me write first here, maybe class on 10:20 to 12. Class is on PR 3011. Okay. Hey, why 301?
No, 12 up 12.
Okay, let me write just one problem here. It's actually related to physics, but let me just write first. It will relate to our calculus. So I have this. We have this function from t0 to t equal 5. So S is distance or position. The question is first average velocity and then average speed. Okay. If you want to work this, you can try. It's related to physics actually, but we will open the new chapter, then chapter 4, through this question. Okay, I think that's it for today. We are going to elaborate this later on. Okay.